So we have huge code bases that are available for research. Now, what can we do with these code bases? We can simply treat them as data. So source code becomes data, and this enables probabilistic reasoning from the existing code bases. Probabilistic reasoning. Just to ensure that you are on track, let's recap what probability is. It is a measure of the likelihood that an event will occur, and probability is always between 0 and 1. A practical example is a coin flip. So I have a 20-cent coin in my hand. The probability of finding heads, which would be this Estonia side coming on top, is 0.5, and the probability of tails is similarly 0.5. Now let's see if heads comes. No, it is tails. Probability distribution extends the concept of probability. On the slide you can see two figures showing the probability distributions. On top, the probability distribution describes the probability of the sum of throwing two dice simultaneously. So we have a white dice and we have a black dice. The probability of getting two ones is, for example, 0.03 roughly. The probability of getting two ones and the sum of two is the same, because there's only one combination that leads to the total sum of two dice being 2. This is the case that they are both 1. We can also see that the sum 3 can be formed with two different types of situations, with the black dice being 1 and the white dice being 2, or the inverse where the black dice is 2 and the white dice is 1. Therefore, the probability of getting the sum 3 from the throw of two dice is higher than the probability of getting the sum of 2. The highest probability for the sum of two dice being thrown is 7. This occurs 1 in every 6 throws. The reason is simply a combination that how 7 can be created is the highest. So this above figure represents a case where a probability distribution is built from the theoretical properties of the dice and the assumption that the dice is fair and unbiased. In below we can see a figure that is built from the data. For illustration purposes, it shows the actual people that are measured. So this is the height distribution of maybe 30 or 40 some people. Females are in white and males are in black, or is this dark blue? The height is given in imperial units, meaning here we have 5 foot 6 inches tall people. We can see that the 5 foot 6 inch is the most popular category overall. However, we can see that most men are actually 5 foot 10 inches over here, and only one woman is that height, and only 2 women are taller than 5 foot 10 inches. If we look into extremes, we can see that there are no women with 6 foot 5 or taller. We can also see that there are no men with 5 foot 0 inches tall. It is obvious from this figure in below that men are taller than women. Therefore, we can use the height of a person to make a prediction about the person's gender. So the idea behind probabilistic reasoning is that we use data to make predictions. So if a person is 190 centimeters tall, we can assign the probability of nearly 1 to the condition that this person is man. On the other hand, if a person is 155 centimeters tall, then we can assign very high probability to the chances that the person is woman. We still remember the example of a coin flip where the probabilities of heads and tails are the same. If we get the person with the height of 169 centimeters, we can see that it is equally probable that this person is either male or female. We use probabilities every day when making decisions and even when speaking. This figure shows what people perceive when they heard, for example, a statement almost certainly. We can see that the assigned probability for the almost certainly is in the medium point is 97–98%. So it is very likely to happen according to these people. We can see that the probability distribution for the statement chances are slight is quite flat and quite wide. It means that people have a lesser agreement on what it really means. For example, in comparison to almost no chance, people mostly agree that it's very, very close to zero. And hardly no one would assign a probability of 30% of the event occurring if one is saying almost no chance. And if the chances about something occurring is about even, we can see that the probability distribution is nicely around the 50%, as it should be. There are many areas of application for probabilistic reasoning. This meme shows different areas of probabilistic reasoning, or where is it applied. We can see that it's being used in statistics, machine learning, and artificial intelligence. Of course, artificial intelligence, machine learning, and statistics are not purely the same thing. Still, they heavily rely on the concepts of probabilistic reasoning, making decisions based on data. The distinguished difference between statistics, machine learning, and artificial intelligence, of course, is that machine learning methods are typically more complicated than the statistical methods, and the artificial intelligence methods are even more complicated than the machine learning. Okay, some time back ago I did some probabilistic reasoning on whether a line of text occurring is natural language or not. The reason why we wanted to do this was that we wanted to do natural language processing on text, and this text was coming from software engineering sources. However, the natural language was mixed with source code, stack traces, and error messages. So we wanted to get rid of the non-natural language text so that we could apply natural language analysis techniques to the actual natural language. Idea 1 was to use deductive reasoning, not probabilistic reasoning. And the idea would be to use regular expressions to make rules to get rid of text that is non-natural. For example, if a line starts with the opening curly bracket, we would always classify it as non-natural. However, when trying this out on a real dataset, it was found to be really difficult to find rules that would be universal and accurate enough. So we went forward with the idea 2, which is probabilistic reasoning. We would define the features using regular expressions and other techniques, but then we would let the computer to learn the weights to determine whether a line of text is natural language or not. When I say features, in the previous example of predicting a person's gender from the height of a person, the height that was measured is the only feature we are using to make that prediction. In the previous example, we could have had other features, such as the weight of the person or the width of the shoulders of that particular person. So to come back to the example of predicting whether a line of text is natural or not, we extracted 11 features. Some of the features are shown here on the screen. For example, in a line of text, the ratio of capital letters was one of the features. We also had a ratio of characters that are not alphanumeric or white space, meaning, for example, a comma or a question mark. We measured the ratio of numbers in the line of text and also the length of the word. Another feature we inserted was the stop words, so the number of stop words in a line of text. Stop words are common English words that occur so frequently that they do not have any particular meaning. For example, the, if, and. Okay, so these were our features. Then we extracted some weights for these features to make the prediction whether a line of text is natural or not. You can see the weights here in above. It is important to look at the sign. So a negative sign predicts that this is non-natural language. For example, for comments, we can see that the features that predict that the line of text is non-natural are the ratio of capital letters, the ratio of specials, the ratio of numbers, and the length of words. The features that predict that it is natural language are the two different types of stop word languages. So this illustrates the idea of probabilistic reasoning. We get a set of weights that assigns a probability for a line of text to be natural or not.